C++, and we'll look at the future roadmap of the project. So, yeah, before we jump in, some quick prerequisites for the hands-on lab. Please make sure that you have Docker, Docker Compose, and Git installed. If you don't have that, please make sure you get these prerequisites installed in the meantime while we go over Presto C++ and Velox so that you'll be prepared for the hands-on lab. And it will also help if you can pull these Docker images beforehand because some of them are quite big. For instance, the first image is for the Presto coordinator, uh, and it's hosted on Docker Hub. So once you do Docker pull, you'll get the right image based on your platform. But the second image, it's for the Presto C++ worker, and it is currently hosted on ECR. And we have images for Arch64 and x64 architectures. And yeah, based on your system architecture, please make sure that you pull the right image. And Ali will be sharing the link for the x64 for the ECR from where you can get the x64 images. So you can pick any tag. Uh, uh, this is the latest tag that was present when the slides were prepared. So if there's a newer tag, please pull that. And if you're on Arch64, we currently have only this image, 289 Ubuntu ARM64. So please make sure you pull that image. Okay, okay, let's get started with a quick background on Presto first. I'm sure most of you are aware of this. Presto is an open source distributed query engine, and it's written in Java. It allows users to run SQL queries over different data sources by providing different connectors. And it has a two-tiered architecture, which consists of a coordinator node and one or more worker nodes. For example, we can see here that there's one coordinator node and four worker nodes in the Presto cluster. So the coordinator is responsible for receiving queries from the user, parsing the SQL, optimizing the query, uh, and it hands off the actual query execution to the worker nodes, which take care of the query execution. The Presto coordinator needs to communicate with the Presto workers, and this is done using the HTTP REST interface. And the workers, they communicate with each other in Presto page format. So the workers, they also have connectors because they should be able to query different data sources. And in this example, we can see that the Hive metastore is being used to sort of act as a bridge between the table schemas and the data files. The data files could be in like object storage like S3 as we see here, and then open data formats like Parquet or ORC. So some limitations with Presto Java, because Presto is written in Java, we don't have a final control over memory because it's managed by the JVM. And we're also not able to use like modern vectorized CPU execution techniques such as SIMD. So that's a big drawback as well. And the JVM also suffers from pauses during garbage collection, which could result in performance cliffs. And all of these were found to be causing several operational difficulties when using Presto. So this is what motivated Presto C++. It started as a full rewrite of the Presto worker in C++. It implements Presto's HTTP interface. This is, in Presto C++, we implement the Presto's HTTP REST interface and the coordinator to worker orchestration and the status reporting endpoints and the exchange protocol and so on in C++. The Presto C++ worker, it can be used as a drop-in replacement for the Presto Java worker. And Presto C++ is built on top of Velox, uh, which we'll take a look at in a while. So let us see what changes in a Presto C++ cluster with the same example from before. So except for the changes in the worker node that we see here, the rest of the Presto cluster architecture remains the same. So we can see that in these workers, the connectors to query these different data sources, they are provided by Velox because Presto C++ is built on top of Velox. And uh, the workers, they still communicate with each other in the Presto page format, and the coordinator is still taking care of parsing the SQL, optimizing and scheduling, and so on. With Velox, some advantages that we get, or we can use vectorized. Velox is Velox uses vectorized execution, so uh, we benefit from uh, techniques like SIMD. We benefit from faster query execution. And Velox also has like other runtime optimizations, uh, which we'll look at in the next slides. And it also has advanced memory management features like memory arbitration. Um, okay, so brief overview of Velox. Velox is an open source uh, unified execution engine which helps to consolidate different data management systems. So uh, it provides different data processing primitives based on the principles of vectorized execution, and it also offers several runtime optimizations. Um, could you could you give me a second, Ali?
Sure.
Uh, yeah, thank you. I'm sorry, I'm having some issues with the screen and with the PowerPoint. So give me just a second. Okay. So yeah, let's look at the history of Velox and why it was started. Velox was started at Meta because they observed that they had like many specialized query computation engines, and they were targeted to like very specific data workloads. And these engines, they did not share much with each other. So it was getting difficult to maintain and optimize all of these different engines and at the same time provide a consistent experience to the user. So Velox was started to address these issues at Meta. And it's a library of reusable, extensible, and highly performant data processing components. And it can be used to build execution engines uh, as we have done in Presto C++. And Velox has also been integrated with other projects like with Spark in Project Gluten and other projects at Meta like PyVelox. So what it does is it helps extend optimizations which previously used to be present on like individual engines to whichever engine is built on top of Velox. So it helps to democratize these runtime optimizations. So let's look at some of the basic components of Velox. So Velox has its own type system and it supports scalar types and complex types. So scalar types are again of two types, physical types and logical types. So the set of physical types is fixed, and the physical types, they determine the in-memory data layout, whereas the logical types, they derive from these physical types and they add more attributes such as like decimal, which adds like precision and scale as attributes. So Velox is vector based. So what it means is all the input and output parameters are vectors, and it supports different vector encodings like flat encoding, constant, dictionary encoding, and so on. Velox also has a fully vectorized expression evaluation engine. It provides APIs for developers to build custom functions, including aggregate functions. So for scalar functions, Velox has a simple row by row interface and also a vectorized interface. And it also has implementations of common data processing operators like table scan, hash join, and so on. Velox has tasks that track memory usage with memory pools. So these memory pools are tracked in a hierarchical fashion, and they're handled by the memory managers. So the users can reserve memory for specific operations, and the memory allocator is going to take care of the allocation. It's going to allocate a contiguous section of memory or a buffer, and the memory manager accounts for all of these. And these buffers, they can be reused across vectors. Velox also optimizes for zero copies during data processing. And coming to IO, Velox provides a generic connector interface, and it can be extended to support different file formats and storage adapters. Popular file formats such as Parquet or C are supported, and storage systems like S3 are also currently supported. So Velox also has a serialization interface for network communication, and it supports Presto's serialized page or Presto page format and Spark's unsafe row format. Uh, Let us look at some of the runtime optimizations in Velox. So if you're evaluating a predicate, Velox can adaptively reorder the conjunct expressions like and or based on their selectivity. So the most selective expression is evaluated first. Velox also allows the developers to define a null-free fast path for functions, and this will be used if the data does not have any nulls. Uh, the hash tables in Velox, they can adaptively use array-based normalized key or hash function mode depending on how many distinct keys there are, distinct grouping keys there are. And for instance, array mode can be very efficient as it does not require you to compute any hash value, and you don't need to compare the new grouping keys with hash table entries. But array mode can only be used when the values of the grouping keys, they can be mapped to a relatively smaller integer range. So that's a drawback, and Velox can adaptively decide this mode for you, and you don't have to worry about it. Uh, when it comes to joins, let's say a join is running in the same stage as the table scan of the probe side. In that case, Velox can filter out the probe rows which don't have a match on the build side. It can push this filter down to the table scan node, and this is referred to as dynamic filter push down, and it's a nice optimization. For aggregations, if an aggregate is not cardinality reducing, Velox can turn off partial aggregation adaptively, and this could help you in cases where partial aggregation would mostly encounter unique keys and it cannot really reduce the cardinality of the data. Another nice feature of Velox is memory arbitration. And this ensures that memory is fairly shared among all the running queries by dynamically adjusting their memory capacities at runtime. And this is done to adapt to changes in the memory usage. So what memory arbitration does is it ensures the total allocated memory capacity of all the queries is within the system configured query memory limit, while at the same time ensuring that no single query runs out of memory. So let's say a query tries to allocate more memory than its current capacity. The memory arbitration will increase the query's capacity. And this is done by either reclaiming the used memory from other queries which have larger capacities, or by pausing live operators using techniques like spill to disk. Okay, so before looking at how Presto C++ uses Velox, let's look at how the Presto coordinator processes a simple query with this example. So this is a variant of the TPCH query 1 on the line item table. So we have three aggregates here, and a group by on return flag and line status, and an order by on those two fields as well. So what the Presto coordinator does in order to execute this query is it converts it into a tree-like structure of plan nodes, which we can see on the right side. And this is called the plan intermediate representation. So for this query, we could have the following three nodes in this order. So the output of the scan filter project on line item, it's going to apply the filter on ship date, and then it's going to pass on the rows to the hashtag operator, which does the group by, and then there's going to be, for instance, a sort node, which ensures that the rows are ordered on return flag and line status. So if you've run a query in Presto before and looked at the query plan, this should look familiar to you. So these are the different stages in Presto. So the Presto coordinator, in order to execute a query, it breaks it down into a hierarchy of stages, which looks something like this. And you can look at the different stages on the Presto console by going to the live plan. And this corresponds to the previous query that we saw. Uh, and here we can see that uh, there are four stages, 0, 1, 2, and 3. We can't see stage 0 here, but it is called the root stage, and it is responsible for getting the output from all of the other stages in a bottom-up fashion. So each stage can be executed in parallel by a series of tasks, and they're distributed among the Presto workers. And each Presto task, it'll have inputs and outputs, and it's executed in parallel using a number of drivers. Uh, and yeah, tasks operate on splits, which are basically sections of a larger data set. So with this background, let's look at how Presto C++ uses velox. So it's Presto C++ is basically a very narrow wrapper service built over velox. And in order to execute a query, it first converts the Presto fragment plan, which has Presto plan nodes, into an equivalent velox plan with velox plan nodes. And then it sets up the resources needed by velox, like thread pools, IO executors, and so on. And then this converted query plan is executed in velox using drivers. Uh, we'll take a closer look at how this is done with our example query. So before that, for some background, let's look at what plan nodes and operators in velox are. So velox query plan is basically a tree of plan nodes, and each plan node can have multiple child plan nodes. So in order to execute a query plan, velox is going to convert this tree into a set of operator pipelines. And each pipeline is going to be made of a linear sequence of operators, which corresponds to a subsection of the plan. So this can simply be done by taking the plan tree and breaking it down uh, by disconnecting all but one child nodes. So you'll get like many different linear subtrees. And the conversion of plan nodes to operators, it's mostly one-on-one with some exceptions. Like if you have a filter node followed by a project node, it could be executed by a single filter project operator. And here we have highlighted the plan nodes and the operators corresponding to our example query. So you can see there's a table scan node in order to read the data, and aggregation to perform the sum and count aggregates, and order by node to sort all the rows on return of return flag and order status, I think. And um, yeah, now let's take a look at how an operator pipeline, how it looks like and how it is executed in velox. So uh, here uh, we have stage 0, stage 1, and in stage 1 we have several tasks. So let's take a look at one of these tasks. Let's say task 0, which is highlighted here. We can see that we have 3 operator pipelines, which is consisting of remote source followed by local exchange and hash tag followed by partitioned output. So a plan node, it can be converted into one or more operators, such as if you have a table scan node, it can be converted into multiple table scan operators, and each operator can be executed by a driver, which is a thread of execution. So, but some plan nodes, they can be converted into multiple operators of different types. Like let's say we have a hash join node, it can be converted into multiple hash probe operators and hash build operators. So sorry, okay, yeah, I'll continue. Please interrupt me if there are any questions. Yeah, task is going to be responsible for receiving splits from the application. It provides access to the different operators. And the splits, they can only be added to the leaf nodes. So the operators that correspond to leaf plan nodes, they fetch and process data. And these operators are called as source operators, such as table scan is one example. So a task in Velox has different APIs. we use the add split API in order to add a split for a particular plan node. And it is the add split API is called multiple times in order to get data. And once you've gotten all the data, you can use the no more splits API in order to signal that you have received all the splits. And that is basically when the task will complete. So yeah, this is a very simplistic overview. And for more details, please refer to the Velox documentation. You can go to veloxlib.io and yeah, check out the docs for more details. Okay. So yeah, what are the benefits of Presto C++ for Velox? So the most important thing is with Presto C++, we get a huge performance boost. So it allows us to run the same queries on much smaller clusters or using fewer resources. So it gives us a better price performance compared to Presto. Uh, a similar initiative is Photon by Databricks, which is also a native vectorized engine written in C++, and it has been observed to provide a 3 to 8x speed up on average. And yeah, with Presto C++, as we saw before, there's no Java processes or JVM, and memory management and SIMD, they're explicitly controlled. And we have advanced features like memory arbitration, which lets us improve the efficiency. And because Velox has reusable and extensible components, it's easier to build and operate at scale across different data engines. As we saw before, there's Project Gluten or Spark on Velox, which has been very successful in addition to Presto C++. And we can also understand the performance and fine tune it in a better way with Presto C++. Okay. So yeah, just summing up, the future of Presto is Presto C++, and this is because it's a full rewrite of the Presto query execution engine in C++, and it's built on top of Velox. We have noticed very encouraging results with Presto C++ so far, with an average speed up of 3 to 4x in terms of performance and scalability. And it has been possible because of community effort across many companies, including Meta, IBM, Uber, ByteDance, so on. Uh, and yeah, the goal of the Presto community and the Presto Foundation is to make Presto the best open data lakehouse engine in the market. And Presto C++ plays a big role in achieving this goal. So we see Presto C++ as the future of Presto, and we are very excited about it. And we are working to make it better and more stable. Um, So next we'll be jumping into the hands-on lab, unless there's any questions.
Yeah, so still currently the coordinator is still in Java side.
Yeah, that's right.
It will continue like that, or
Yeah, it's gonna continue like that
okay,
for the
only the
foreseeable
workers,
future.
only the workers will be in the
Only
C++.
the workers, right, yes.
Okay, okay, thank you.
Okay. Yeah, let's go to the hands-on lab. So I'm assuming everyone has Docker and Docker Compose installed by this point, and if you manage to pull the Docker images, that's great. Otherwise, we can do it now. So yeah, before we jump into the lab, we'll just take a quick look at some of the technologies we'll be using here. So Docker Compose, it's a tool for defining and running multi-container applications. So in our hands-on lab, we'll be using Docker Compose with one Presto coordinator container and two Presto C++ or Presto Java worker containers. And for this demo, we'll be using the local file storage using the file-based Hive metastore. And we'll be using pbench to run benchmarks against the Presto cluster, and this will be interacting with the Presto coordinator in order to run benchmarks, and we'll look at pbench in a while. Okay, so yeah, pbench, it's a new open source benchmarking tool for Presto. You can find it under GitHub Presto DB, and you can use pbench to run benchmarks for like different data sets like TPCDS, TPCH, and so on. And you can also create your own custom benchmarks by providing a JSON configuration file. And it supports multiple stages, random query orders, and cold and warm runs, and so on. And you have different util commands to compare results, generate data, make sure that the row count is as expected, and so on. And yeah, pbench is written in Go.
Pramod, one quick question. Abbas is asking, what is a local exchange?
What is a local exchange in in Velox? Or let me go back to the slide. Okay, so yeah, I mean, in this case, you have data from your split and it's going to be distributed among these different operator pipelines. So that's what happens in local exchange. So your data, so your data is kind of divided into these different pipelines, so they can sort of execute it in parallel.
So actually, the question is a little bit around because I guess local exchange is, I think, privy to I think Presto. So I mean, if local exchange is about splitting up, I mean, giving splits to different maybe task instances, then I guess the execution engines would also have the similar concept, right? But they don't, which means that there's something specific, very unique to Presto about the local exchange, which is not there in other databases. Am I asking the right question?
Um, I'm sorry, I couldn't follow. Could you please repeat?
So so I think task parallelization or split or parallelization on the split boundary. I mean, that is not
Okay.
only a Presto specific thing, right? It's a common across all databases. So if the local exchange operator is meant to sort of let's say create different task instances per split, as you mentioned, then and that's the functionality of the local exchange. Then what is the equivalent of, let's say, a local exchange in, let's say, another execution engine? Let's say
Like
Spark or
Velox?
something.
No, but like in this case, right, Velox is going to get a split, and it still needs to use, it still has its own parallelism. It still has its own mechanism to execute queries in parallel using like drivers, right? So I think this is specific to Velox, uh, and um, yeah, I'm not sure how this exactly maps to Presto. I would need to look at the documentation for that.
Okay. I mean, the reason I'm coming is because I remember seeing a rule in Presto DB called add local exchanges. And that's what seems to
Okay.
add the local exchanges to the plan of Presto. So, I mean, I was just trying to map that as to what the actual local exchanges add rule does, and what is the meaning of an of a local exchange, and that's where I'm coming from.
I think from what I understand, it's within a single worker, right? So you'll still want to get parallelism when you're running like a query in a single worker, and you'll still need different drivers to work on different parts of the data. So from my understanding, that's where it comes in.
Okay.
Uh,
Okay.
yeah. Sorry. Not sure if that answered your question, but yeah, I would need to look at the docs uh, for more context on yeah on the Presto side of it.
Okay. Thank you. Thank you.
Yeah. Okay. Yeah. So yeah, for the Presto C++ lab, we're going to go to this website, which has all the steps, and we'll follow along the instructions there. Uh, so let's jump to part one, where we'll deploy a Presto C++ cluster using Docker Compose. And yeah, if you haven't pulled these images, we can do it now when we run Docker Compose. So, okay, so we'll be cloning the Prestorials repository. It's also under Presto DB. So please make sure, yeah, I'll open the terminal and we'll just follow along these steps. So if you have a doubt at any point or you run into any errors, please let me know. So I have a Linux VM which has an Intel CPU x64, and I'm using a Mac M1 which has ART64 architecture. So we'll be deploying a Presto C++ cluster on both systems, and we'll be running pbench on both. So you have two terminals open with split panes. This is for running Presto CLI or pbench, and this is for running Docker Compose. Okay, so I'm in our temp directory. I've named it lab and it's empty, so I'm gonna clone the Prestorials repository here. Now we're gonna go into Prestorials. So yeah, that's the first step. And the second step is basically about using Presto CLI, which if you have done it before, you should be aware how to run Presto CLI and submit queries to Presto. But yeah, in this case, we won't be downloading the jar. Instead, we already have a Presto CLI on the coordinator container. Once we, once we have a Presto cluster up and running, we'll be able to use the Presto CLI from the coordinator port. So we'll come back to this. And yeah, before that, we are going to generate TPCH and TPCDS data using Presto Java's connectors. So because we're using the file-based HMS, the data will be present on the local file system. So we'll navigate to the appropriate directory, which is Docker Compose local file system. And because we're deploying so what we'll be doing first is we'll start a Presto Java cluster with a single node. So the coordinator is also going to be acting as a worker in this case, and we'll generate this data using Presto Java. So we'll go to Docker Compose local fs, and we have this Docker Compose file, Docker Compose single node.yaml. So we'll be using that to start a single node Presto cluster. But before that, because we'll be generating a lot of data, we would want to increase the container memory limit from the default of 2 gigs to 10 gigs. So let's do that. Please navigate here and change this to 10 gigs. And also, the default platform here is Linux ARM64. So please modify this to AMD 64 if you're using x64 platform. So yeah, with these changes, we're ready to run Docker Compose. So let's wait for the server started message. Okay, so let's confirm that from the Presto console that we have an active worker, and this is on my local system, and this is on the my bad. Yeah, the Zoom tab seems to be interfering. Let me pull it a little down. Okay, so we have the cluster running on both, and now we're going to Presto CLI. That's going to be on the containers. So so your container is going to be named Presto Servo. You can confirm this by running docker ps.
Pramod, we lost your screen.
Oh, okay.
I can see your screen.
Oh, sorry. Yeah, I didn't realize that.
It's visible.
What about now?
Yep.
Okay, cool. So let me log into this VM again. Okay. So now that you have your Presto coordinator / worker running, we're gonna use Presto CLI from this container. Uh, so because it's named Presto _ server, so we do docker. Gonna log in to this and run Presto CLI there. But before that, let me make sure it's run on boot. Yeah, so we have Presto CLI, and let's see what catalogs we've got. And yeah, we have the TPCDS and TPCH catalogs. So we'll be using CTAS queries in order to insert data into the Hive catalog, Hive and Iceberg catalogs. But for this lab, we'll be using the Hive catalog in order to run benchmarks. And yeah, we'll be using these SQL files. So let's come out of Presto CLI. And yeah, let's download these SQL files first. We'll only download create Hive TPCH tables and create Hive TPCDS tables. But for because we'll only be running TPCDS benchmarks, this should be enough. Create Hive TPCDS table should be enough. So let's just do this. And then we'll copy this to the container so that we can pass this on to Presto CLI as an argument. We had the container ID here. So we're going to copy the container ID. And going to copy it into the root directory. This case, this is the container ID. This is Hive PPCDS. Okay, so now we have copied this file containing the CTAS commands into the container. So let's take a look at what these CTAS commands are. So these have been borrowed from the existing end-to-end tests in Presto. So nothing new here, but let's let's take a look at this SQL file. So what we're doing is under the Hive catalog, we are creating the TP-CDS schema, and we're we're creating tables in the schema in hive.tpcds from by copying data from the TP-CDS connector. And in the TP-CDS catalog, we have different schemas corresponding to different scale factors. So we'll be using a scale factor of 1 for this lab. So it's a simple CTAS command. Some of the changes here are because Presto C++ currently does not support the char data type. We're just converting the char columns into varchar. And that's pretty much it. We're just doing this for all the TP-CDS tables. Okay. So now we'll go to the next step. Is everyone able to follow along till now, or are there any doubts? Okay. Yeah, then we'll go to this section. Because we want to generate just TP-CDS data in Parquet file format and Hive table format, we'll use just the CTAS queries from this SQL file. And feel free to generate TPCH schema as well if you're interested. But yeah, we'll just run this command for now. And containers name Presto servers. Yeah, this is if you've used Presto CLI with the file argument before, we're basically just passing this file as an argument to Presto CLI and running all the SQL queries from those files. I'm going to run this on both. Okay. So we can see that these tables are being created, and we can also go to console to make sure that these queries are running on both the clusters. So this is on my local setup and this is on the Linux VM. We'll wait for these tables to be created. It could take a while. There is another option if you don't want to generate this data with Presto Java. It's already present on S3. So you can just download it from here by going to this link. You'll get a data.tar. You can untar it and you'll be all set. But this has also been generated using Presto Java, so it might be better to just do it completely end to end without downloading the data from anywhere.
What is the data database? It is in the S3?
Yeah, right. I think it's this link. I'm sorry, it's just hosted on S3.
Okay.
Yeah, the data format itself is Parquet, and it's with the Hive connector, so the table format is Hive.
Okay.
Yeah, it's just hosted on this link. Yeah, if you don't want to generate the data using the CTAS commands, this is a simpler way to go. Yeah. So the data generation is finished on my local device, but still going on in the VM. So let's continue on to the next steps on this device. So let's So yeah, the next step is going to be this data has been generated on the Presto server container, which is running. So we need to copy it into our local device because the Docker Compose file, it's going to want this data directly to reside in this path, Docker Compose local FS. So we have to copy it from the container to the local system. So we'll be using Docker CP. We have generated Hive data, so it's going to be in home Hive data, and we'll create a data directory in Prestorials, and we'll copy it into this data directory. So it's like this is also mostly done, but we'll continue with this. We'll go to Prestorials, create a data directory. Then we're gonna get the container ID and copy the data from the container. It's gonna be in home Hive data because if you go to the config, this Docker Compose file, it gets hive.properties from here. And you can see that the Hive metastore directory is set to home Hive data. So so the data will be generated here from the ctask commands that we saw before. So we'll be copying the data from this container to our local system. Okay, so now if you go to data, you should have Hive data, and if you go to dpcds, that's going to be the only schema. You can see that the tables are all present. Let's say you can go to call center, make sure that the data is there. And so now we have our data directory. Let's do the same thing on the Linux VM as well. Yeah, if you have any questions or if you run into any errors, feel free to interrupt at any time. So this is the only time-consuming step, and the rest of the lab should be pretty straightforward.
While we're waiting, I'll just repeat because RJ asked a good question. What's the roadmap availability for using in production? So I dropped in the link. There are some supported use cases right now where you can run Presto C++ in production, and that link is in the chat. We're actively working on expanding those use cases, right? And so I'd say, a call to action is join this movement if you are interested in being a part of the community. There's a lot of work that we're doing, that the community is working on. And by the way, this is a cross-functional community effort. So it's not just one company, right? It's IBM, it's Meta, it's Uber. It's a bunch of companies that are working together to get this to a place where it will be much more widely available to run in more general use cases. But today we do support, the Presto C++ does support some specific use cases. And like I mentioned, Uber, Meta are both using, and a few others are using Presto C++ in heavy production at their companies. And there's presentations on this too. I'm happy to share if you're interested.
Thanks, Ali. Okay, so yeah, now we got the data downloaded. We have the data directly in Prestorial, so we'll continue the rest of the steps. So yeah, the next step is we're gonna deploy Presto C++. And because we're using the file-based HMS, we'll need to copy the data into this path first. This is because if you look at the Docker Compose file that we'll be using to spin up the Presto C++ cluster, it mounts this data directly into home, and that is where the Hive connector gets the, that's the catalog dir for the Hive connector with the file-based HMS. So because this points to home Hive data, we'll need to copy it from current directory, which is Docker Compose native local fs to home. So now we'll be going to Docker Compose native local fs, and we'll just copy this command. For ARM64, please use the ARM64 Docker Compose file. For x64, please change it to AMD64. So you have the right Docker Compose file. So, okay, we'll need to, I forgot to bring the previous cluster down. Yeah, please make sure that you bring down the previous cluster because the network is going to have the same name. Otherwise, you wouldn't be able to start the Presto C++ cluster if you have the Presto Java cluster still running. Now we're gonna go back to Docker Compose native local fs, and we'll now run the Docker Compose. As before, we're gonna modify this to AMD64. And let's go to the console, make sure that it's up. Still don't have any workers. We'll need to wait for the announcement succeeded message, log message here. Yeah. So we have workers in both of the clusters. Now we're going to use pbench next in order to, now that we have a Presto C++ cluster, we're going to run tpcds benchmarks with pbench. So for that, we're going to jump to the next section. We're going to come back to this to deploy a Presto Java cluster. But before that, we want to get the benchmarks with Presto C++. So yeah, again, you have, you can find pbench under PrestoDB pbench, but if you go to releases, you'll have like different releases based on your platform. So please make sure you download the right pbench based on your platform. So for so this is part 64. So I'm downloading this version, but here I'm going to download Linux x64. And now you should have pbench.tar. So untar it. Then you can get rid of the tar. Now go to pbench. Because we are going to be running TPCDS benchmarks with SF1, and our catalog is Hive and the schema is TPCDS, we need to make sure that in the corresponding JSON file that pbench is going to use, we set the appropriate catalog and schema. So go to benchmarks. We're going to be running TPCDS. So benchmarks TPCDS SF1.json. And by default, it is set to TPCDS catalog and SF1 schema. So please modify this to Hive or TPCDS. And once that's done, you're all set to use pbench. So because this is a Presto C++ cluster, we're just going to run this. So what pbench does is it submits each query sequentially, and the queries are defined in dspower.json, which is, if you look at this command over here, it's in benchmarks tpcds dspower.json. So if you look at this, you have all the different queries, the 99 TP-series queries, and the expected row counts for each. So pbench is going to validate that the number of rows returned by Presto matches this expected row count. And if we go to the Presto console, we can see that each of these queries, it's being submitted and run one by one. It looks to be much faster on my local device than the VMs. So in the interest of time, I'll just I'll stop running commands on both, and I'll just switch to my local system. But you should be able to proceed even if you're on Linux x64 without any issues. But if you do run into any issues, let me know. So now if you go to this directly that's created native OSS SF1 DS Power, you'll see a CSV file with the execution summary. So So, okay, this is where my pbench is. So if I go in here, and open the CSV file. Okay. So here we can see the row count and the start time, end time, how long the query took, and corresponding queries. So we'll save this. We'll create a new Excel file and copy this and the duration because we want to compare this with Presto Java. So this is going to be and close this. And we're going to go back to this terminal. We'll bring down these clusters. And now we'll spin up a Presto Java cluster. Again, it's going to be a similar Docker Compose file, and I'm just going to run this one. But yeah, if you're on x64, please run this, use this Docker Compose file. And I don't have the data directly. So I just copied the data directory from Prestorials into Docker Compose localfs because that's the path that will be used by this Docker Compose file to start a Presto Java cluster. So once it's up, we are going to run pbench again. We're going to use pbench to run the TPCDS benchmark again with this Presto Java cluster and get the numbers for Presto Java. So this is the command. Let's make sure cluster's up and running. It is. So go to pbench. We have already modified sf1.json. So to hive.tpcds. So we're just going to run this. And we'll make sure the queries are passing. Looks like they're running fine. This could take a while because it's Presto Java. So we'll wait for this to complete. In the meantime, if you have any questions, please let me know. I hope everyone's able to follow along with the hands-on lab and you got the numbers for the Presto C++ cluster, the benchmark for Presto C++ using pbench.
So has anybody gotten this far? Has anybody been able to follow along? You can just let us know or do a thumbs up or something. Anybody?
Sorry if this was too fast, but yeah, you can access this Presto Native Lab at any time or do it at your own pace. And
Yeah, we prefer to do it offline.
Okay, yeah, sounds good. So while this is running, we can take a look at some of the benchmarks that we have got. So yeah, the end goal of this lab is to note down the speed up that you were able to measure using pbench, with Presto C++ over Presto Java. So we'll get to this part, but let's look at the speed up that we have been able to get with like larger data sets with again the TPCDS benchmark with larger scale factors. So these are the results for TPCDS SF1K, which is 1 terabytes in size, and with Presto C++, and this was with Presto version 288. Now we are on 291, and yeah, with Presto C++, the total runtime was 31 minutes, and with Java it was close to 1.2 hours. So speed up is more than 2x here, and this is for each query. The runtime comparison. And this is the duration comparison in terms of the ratio. And this is for TPCDS SF10K, 10 terabytes in size, and with Presto C++, all the queries could complete in about 2 hours. With Presto Java, it took about 3.5 hours. So still get a decent speed up with Presto C++. Yeah, and this is with 8 workers in the cluster. This is with 16 workers. Um, Again, the duration ratios. So like for query 16, you can see that it's Presto C++ is much faster. And yeah, this is with SF100K or 100 terabytes data size. And with Presto C++, the total time to complete all these queries was about 4 hours. And this was a result of benchmarking with IBM's watsonx.data, with the Presto engine in IBM's watsonx.data. So for if you're interested um, to learn more about these numbers, please go to this blog announcement to learn more. And yeah, let's see if it has completed. Okay. So, running query 72 now. So what we want to do is like get a similar graph, get a graph that looks like this. So we are going to get the numbers from pbench and we'll wait for it to complete.
I think the key point here is the memory utilization, memory management.
Right, definitely. Yeah. Query 72 seems to be stuck. I don't know why. I think it's gonna complete. It's probably gonna take a while. you can use a smaller scale factor as well, like tiny, if you want to modify the SQL queries in the CTAS file, just modify it to tpcds.tiny, so it runs faster and you don't have to wait as long.
Is the work in C++ ready to be put in the production?
Uh, well, we're already using it in production,
Mhm.
but we're using it internally right now. We're, uh, yeah, we're planning to put it in production for like other clients soon.
Okay.
Yeah. Okay, so yeah, all the 99 queries have completed with Presto Java. So let's go to let's get the CSV file from here. Again, it's gonna look similar to what we saw before. We're just interested in this duration. So I'm gonna copy this to here. So we can get a chart out of Excel. Let's just get a duration ratio chart. Okay, this is perfect. So, um, so yeah, this sort of shows the speed up that we get with Presto C++ over Java. Like if you look at the run times, it's almost always lower than Presto Java. And in the case of query 72, as we saw, it took a long time, so it's a significant speed up. And we can also just sum it up and so yeah, the total time with Presto C++ is close to 88 seconds. With Presto Java, it's about 463 seconds. So it's like close to 5x speed up, which is pretty good. Scale factor of 1. So um, yeah, that's pretty much it about the hands-on lab. Let's go back to the presentation, look at the future roadmap. So um, yeah, right now the focus is on enhancing the usability, and we are working on SPI v2 to provide better support for Presto C++ clusters in terms of functions, expression evaluation, and so on. And we are working to improve the iceberg support. Uh, and yeah, the main focus is on stability with Presto C++. Uh, yeah, I would encourage everyone to please join our community. Please go to prestodb.io. You'll find links to GitHub, Slack, LinkedIn. We have meetups uh, in uh, in the US, in Bangalore, and yeah, please check us out. Join these meetups. Let us know how you're using Presto and what use cases you're looking for. And yeah, for Presto C++, if you're more interested, there's a native working group meeting that happens once every 2 weeks. and you can join this meeting. You can add it to your calendar and contribute to the future direction of the project. And yeah, please check out Velox on GitHub, and there's a Slack channel as well. So please go to veloxlib.io to get the links. And yeah, I'd like to thank all of our partners from the Presto and Velox teams from so many companies like Meta, Uber, IBM, Intel, ByteDance, and so on, who have made this a successful project and who have kept the momentum going behind the project. And I'd like to thank everyone. Thank you. That was it from me.
Thanks, Pramod.
Thank you.
All right,
Thanks, Ali.
folks. That wraps us up. So this was our final workshop in our series, and we appreciate everybody who attended. I know it's late for many of you, so double thanks for that. Hope this was helpful. As Pramod mentioned, we're working really hard on C++, and we're really excited about the results so far. And I think there's a lot more work to do, but it's a testament that some of the biggest companies in the world are using C++ in production at their companies. So we believe the future of Presto is Presto C++, and we do events like these to kind of show what we're doing and to teach people that may not know what's going on in the community and the work being done. So I'll just end by saying, as we all know, Presto is an open source project. It's a Linux Foundation project, and a big part of making sure Presto works is that we have a really good community around it. And so we welcome anybody to join the community, whether it's using Presto, at your company, or contributing back to it in many different ways, writing docs or actual development. We appreciate all of that, and we love all of that, and we really encourage you to share more with the community on what you're doing with Presto. It's really great. Okay, with that, thank you again. If you're here, you're probably already on our mailing list. We'll be doing more events like these. We'll be doing meetups in person around the world, so make sure to join your local meetup group as well, and we look forward to hopefully meeting one day in person. But until then, thanks again, and we'll see you virtually for sure. Thanks, Pramod.
Thank you. Thanks everyone for joining. Thanks, Ali.
Thank you.
Cheers,
guys.
folks.
Appreciate it.
Thank you.